How many numbers are there, truly? This question may sound obvious and ridiculous. One could say infinitely many by pure intuition, and they won't be wrong. However, the more we think about this question, the more ambiguous it seems. You might not see this at first, but allow me to make a case here. If the question refers to how many numbers can we count with, then the set of numbers we're talking about are the natural numbers, denoted by the letter n. 1, 2, 3, 4, and so on indefinitely. Since we can always add 1 to the last number, this list clearly is infinitely long. Okay, but if we're allowed to always add 1 to any number, why shouldn't we be allowed to always subtract 1? By doing so, we enter a completely new realm, and of course, similarly to adding 1 endlessly, we can keep subtracting 1 forever. We call this new list the integers, and we denote it with a z. Once again, we notice these new numbers extend indefinitely to the right and to the left, making it also infinitely long. Now, I want you to think about the following question. Which of these two lists of numbers is bigger? They're both infinite, so it doesn't seem intuitive how either would be bigger than the other. But at the same time, it kind of feels wrong for them to have equal length. After all, the integers contain all natural numbers plus all negative integers. If anything, it should be at least double the size, right? If you don't see a clear answer to this dilemma now, don't worry, these concepts are pretty hard to grasp. What I'm going to attempt in this video is to show you how there's actually a reasonable solution to this question. I apologize in advance since I'm going to spoil the answer here to make an important remark. These sets of numbers actually have equal length, and I'll prove it to you, but what I want to make clear from the beginning is that we have to be extremely cautious when working with infinities, because a result that might seem correct at first could be completely wrong, and vice versa. For now, it's better if we step back a bit and develop a more rigorous framework to work with. Let's begin by laying down some useful and necessary definitions. In mathematics, we usually talk about elements and sets without giving much thought into what they actually are. A set, simply put, is a collection of elements, while elements are, well, they can be anything. Numbers, matrices, functions, even other sets. We aren't interested in the ontological definitions as much as we are in the properties and tools we can derive from them. For the sake of clarity, I'll present a few symbols that mathematicians use frequently when developing theory. To write that an element x belongs to a set A, we use this symbol and we read the expression as x in A. To denote the opposite, that is, if x doesn't belong to A, we write it this way and it's read as x not in A. Brackets are used to indicate whenever we're defining a set. For example, let's say A equals a set containing a square and the number 0. We can write statements such as 0 is an A and pentagon is not an A. If we define a new set B containing again a square, the number 0, and a two-dimensional vector, we see that all elements of A, namely the square and 0, are also elements of B. When all elements of A are also elements of B, we say that A is a subset of B, and we represent it symbolically as such. For now, we haven't really done much other than presenting some mathematical notation, but let's start getting used to how to write logical statements. There are two symbols that are extensively used in mathematical propositions. First, we have the for all symbol, which, as the name suggests, we use it to describe a property that all elements of a set satisfy. We call it a universal quantifier. As an example of its use, the definition for a subset in logic notation would be A is a subset of B if and only if, for all elements A in A is also in B. This double arrow makes this a biconditional statement, and it means that the left and right sides are logically equivalent, or in other words, that if one is true, the other one is as well. You don't have to understand this fully for now, just bear in mind that we use this symbol to create definitions. Next, we have the existence symbol. We use it to emphasize when there's at least one element that satisfies a particular property. We call this an existential quantifier. As an example, notice how even if the square and the number 0 are elements of A, the vector 1, 2 is not. So, since there exists an element in B that isn't in A, this means that B is not a subset of A. It's worth opening a parenthesis here and point out a relevant detail. If we define the statement P as B is a subset of A, that makes statement P false, which means its negation is true, namely the statement not P, equivalent to B is not a subset of A. If we were to write down both statements using the notation we just learned, we could rewrite P as for all B in B, B is in A, and not P would be there exists B in B, such that B is not an A. Observe how there is an inherent relation between the universal and existential quantifiers. When negating a for all statement, we get a there exists statement. Why does this happen? Picture it with this example. Say we have a collection of blue balls and a pink one. If I said all balls are blue, this would be a false statement because there exists at least one that isn't blue. On the contrary, if all balls were blue and I said there exists at least one that isn't blue, this would be false because all of them are blue. This is a fundamental property of quantifiers, and we use it to prove all kinds of statements. Let's take a few minutes to understand how these concepts can be applied with a formal example. First, we define the empty set as that which contains no elements. My proposition is that the empty set is a subset of the previously defined set A. This claim seems pretty bald at first glance. After all, the empty set has no elements to compare with the set A. How could it possibly be a subset of any set in the first place? Well, let's not get fooled by first impressions and try to understand the true nature of this statement. Let's suppose the proposition is false, meaning the empty set is not a subset of A. If we follow up logically, this means there has to exist an element of the empty set that is not an element of A, because negating the universal quantifier turns it into an existential one. But this isn't possible, since the empty set has no elements to begin with. By assuming that the empty set is not a subset of A, we concluded that there exists an element in the empty set, which of course is a contradiction. Therefore, the empty set must be a subset of A. What we just did is called a proof by contradiction. Fitting name, right? Statements such as the empty set is a subset of A are called the vacuous truths. These are propositions that are logically true since assuming a false premise results in a contradiction. Additionally, notice how the fact of using the set A was completely irrelevant during the proof. We could have chosen the set B or any other set for that matter, and the conclusion would not have changed. Since the choice of the set doesn't matter, this means that the empty set is a subset of any set we can come up with, including itself. Now that we have established some basic notions, let us take a look into two key definitions that'll help us better understand the nature of infinite sets. I've already talked a little bit about the power set in a previous video, but didn't really give much detail into what it is. Consider the example of the set A containing the square and the number 0. One interesting question we can ask ourselves is, what are all the possible subsets we can extract from A? Well, since the set A consists of only 2 elements, that means the only subsets we can extract will have 0, 1, or 2 elements at most. The only subset of 0 elements is, of course, the empty set. The subsets of 1 element are the ones containing only the square and the number 0. And finally, the only subset of 2 elements is A itself. The collection of these 4 sets is called the power set of A. We recall that B was defined as a set containing a square, the number 0, and a 2-dimensional vector. So, the power set of B would be as such. We can point out an interesting detail here. The power set of A 2-element set, has 4 elements. For B, a 3-element set, its power set has 8 elements. Can you take a guess on how big the power set of a 4-element set will be? I encourage you to think about this question before I give the answer. As a hint, notice that we can write 4 as 2 to the power of 2, and 8 as 2 to the power of 3. As many of you might have already noticed, the size of the power set equals 2 raised to the power of whatever the size of the original set was. In other words, if S is a set with n elements, there are a total of 2 to the power of n subsets we can extract from S. This is true for all finite sets, including the empty set. Clearly, since the empty set has no elements, the only subset we can extract from it is itself. And surely enough, 2 to the power of 0 is in fact 1. Pretty cool, right? Now let's be a little more creative. Let us redefine the sets A and B, since that way it'll be easier to see the path we'll take here. Consider A and B sets of colors, say A contains red, blue, and yellow, while B contains black, white, and gray. If the colors of A and B represent the colors of shirts and pants respectively, then by associating each element of A with an element of B, we are able to create different outfits. Red shirt with black pants, red shirt with white pants, red shirt with gray pants, and so on and so forth. Notice we've created an entire new set of elements from associating the sets A and B. We call this new set the Cartesian product. In the language of logic, we say that A cross B is the set of ordered pairs A, B, such that A is in A and B is in B. There's an important detail to observe here. The set A cross B is not the same as the set B cross A. Surely, it isn't the same outfit if you wear a red shirt and black pants than if you wear a black shirt and red pants. This is why the elements of a Cartesian product are called ordered pairs, as in the order of the pair matters. To make it a little more interesting, we can consider the set of integers z and construct the cross product with itself. This will result in a set of ordered pairs where both entries are integers. Geometrically, we can look at the Cartesian plane and draw every single point that corresponds to each ordered pair. We are in shape now to talk about one of the core concepts in all mathematics, and one that will help us logically to conclude how the natural numbers and integers have the same amount of elements. To properly motivate the idea, let's return a bit to the definition of the Cartesian product. Consider A as a set of natural numbers and B as the set of numbers in the form of 1 over n, where n is a natural number. For this example, assume that we're interested in finding out which pairs of numbers between A and B result in a whole number after multiplication. For example, 4, 1 over 1 and 4, 1 over 2 are both pairs of interest since 4 times 1 over 1 is 4 and 4 times 1 over 2 is 2, both whole numbers. If we calculate the Cartesian product between A and B, the ordered pairs we're interested in are now those colored in green. By defining a new set R containing these colored pairs, we'll have constructed what mathematicians call a relation. In the language of set theory, a relation is simply a subset of the Cartesian product between two sets. Intuitively, you can think of it as a rule by which we associate elements between sets. If a pair A, B belongs in a relation, we say that A is related to B, and we denote it like this. Now, from all possible relations one could define, there is one in particular worth studying for this video. To begin, I want you to pay close attention to the expression on screen. I'm sure most of you have encountered something similar in math class or in a book. We usually read this as f of x equals square root of x. The letter f represents what we call a function, and x is a variable we decide the value for. This expression indicates that the value of f of x is given by the square root of x. So, for x equal to 2, f of 2 is square root of 2, roughly equal to 1.414. In the case of x equals 16, f of 16 equals 4. If we assume x to be a natural number, we can associate every number x with its corresponding value under f, and as you can probably already guess, we can extract these pairs from the Cartesian product between n and the real numbers, denoted by the letter r. In other words, our function f represents a relation between two sets. We usually denote functions indicating the set from which we initially take a number, in this case that corresponds to n, and the set to which the function sends the numbers, which corresponds to the real numbers in the example. The set n is called the domain of the function, and the set r is called the codomain. What's unique about this particular relation is that the only possible pair for an element of the domain is a square root. This wasn't the case with the first example shown, since elements of A were allowed to be associated with more than one element of B. When a relation only allows elements of the domain to have one single pair, we call it a function. An important clarification here is that functions are allowed to have elements of the codomain with multiple pairs. As a quick example, if we define a function f from z to z, given by f of x equals x squared, notice how both positive and negative integers map to the same value. Here, every element of the domain has one single pair, but elements of the codomain have two. Finally, let me introduce one last useful piece of theory before diving into counting infinite sets. There are three fundamental types of functions: injective, surjective, and bijective. Injective functions are those who associate one and only one element of the codomain to an element of the domain. This definition can be a little confusing at first, since it sounds very similar to the original definition of a function. Allow me then to give a visual example to clarify what injectivity truly is. Consider a and b both equal to the set of integers, and let us define two different functions f and g. We'll define f as f of x equals x squared, and g of x equals 2x. First, notice how the function f sends both positive and negative numbers to their positive squares. both 1 and -1 are mapped to +1, 2 and -2 are mapped to +4, 3 and -3 to +9, and so on and so forth. This is precisely where we need to be very careful with our definitions. F is in fact a function, since every element of the domain has one and only one pair, but it is an injective one, since there are elements of the codomain with more than one pair. On the contrary, G associates positive numbers with their positive doubles, and negative numbers with their negative doubles. Because of this, each element of the domain has one pair, which makes G a function, and so does each element of the codomain, which makes it an injective one. In the language of logic, we may write that a function f from a to b is injective if it sends different elements of a to different elements of b. Or, in other words, if a1 is not equal to a2, then f of a1 is not equal to f of a2 for all a1 and a2 in A. I'd like to add a quick note here. You may see this definition written in its contrapositive form, namely, if f of a1 equals f of a2, then a1 equals a2. This follows directly from the logical equivalence of P then Q and not Q then not P. Following up, surjective functions are those for which all elements of the codomain have at least one pair. Consider the functions f and g as previously defined. Since b is a set of all integers, odd numbers are left without a pair under g, as g only maps to even numbers. On the other hand, f squares all numbers, so no negative integer will have a pair under f. This means neither f nor g are surjective. In light of this, let's define then a new function h given by h of x equal to x. Notice how h sends every integer to itself. This means all elements of b have at least one pair, hence h is surjective. In the language of logic, we say that a function f from a to b is surjective if for all b elements of b, there exists a in a such that f of a equals b. To finish off this section, a bijective function is one that's both injective and surjective at the same time. To put it in simple terms, if a function pairs elements of the codomain to one single element of the domain and none are left without a pair, then we call it a bijective function. The function h is an example of a bijective function. No elements of b have more than one pair, and all elements of b have one pair and one pair only. Try to come up with examples of functions that are injective but not surjective, and vice versa. Play around different sets you might know, or define your own sets. These exercises will help you a lot in case you find yourself struggling with these concepts. At last, after all those definitions and propositions, we can finally formalize what it means for two sets to have equal size, and consequently generalize this to infinite sets. To properly motivate the definition, imagine the following scenario. In front of you, there's two boxes with different objects. You don't know how many objects there are, but you can't tell there's too many to even take a guess. If you were asked to determine whether the boxes had the same number of elements without counting, how would you do it? Take a moment to analyze this question, since it's strongly related to how we'll prove that the natural numbers and integers contain the same amount of elements. It's possible to come up with different solutions to this problem, but I'd like to present one that mathematicians use extensively. We begin by taking elements of box 1 and pairing them with elements of box 2. After a while, we'll eventually reach one of the following scenarios. Either we run out of objects from one box but still have some left in the other one, in which case we conclude they don't have the same number, or we end up with all objects from both boxes with a pair, which implies they have the same amount of elements. I'm sure you've already recognized why this particular method results useful. Indeed, the process of taking an element of box 1 and pairing it with one of box 2 is the same as constructing a bijective function between the boxes. This fact leads us directly to the following definition. Two sets A and B are said to have the same number of elements if there exists a bijective function f from A to B. For the sake of having a different way to refer to the number of elements in a set, we'll redefine this concept as the cardinality of A, and denote it as such. So, the cardinality of A equals the cardinality of B if and only if there exists a bijective function f from A to B. With this, we have finally formalized what it truly means for two sets to have the same amount of elements. Now, in order to prove that the natural numbers and integers have the same cardinality, we just need to find a bijective function between them. As a small note, there are infinitely many bijections we can define between these two sets. As an exercise, pause the video now and try to find one. And if you're already familiar with proofs, I encourage you to attempt to prove that your function is indeed a bijection. For those who are just here to enjoy the show, notice how we can arrange the natural numbers so that each of them pairs with one and only one integer. As this diagram suggests, we first pair 1 with a 0, then all even numbers will be paired with their respective halves, while odd numbers will be mapped to the negative integers. Formally, we can define f from n to z as follows. F of x will be equal to x over 2 if x is even, and if x is odd, f of x will be equal to 1 minus x over 2. By plugging in some values, we see how this function correctly follows the arrangement we established before. Now, even if it's clear from the diagram that f is in fact bijective, diagrams and drawings are not formal mathematical proofs. So, let's go ahead and actually use the definitions we created to prove once and for all that the natural numbers and the integers have the same cardinality. We start our proof by proposing a function f, which in this case we already did. What's left for us to do is to prove that f is bijective. So, we have to prove that f is both injective and surjective. To prove injectivity, we'll recall that f is injective if x1 not equal to x2 implies f of x1 not equal to f of x2 for all x1 and x2 in n. Since we want to prove a condition for all elements of n, what we need to do is take two elements at random, x1 and x2, that satisfy our premise, namely x1 must be different from x2, and we should be able to conclude that they map to different elements of z. In this case, f is defined separately depending on whether x is even or odd. So, we shall then analyze each possible case and conclude how, in all of them, x1 and x2 always map to different numbers. There are three relevant cases to analyze. Either x1 and x2 are both even, both odd, or one of them is even and the other one is odd. If both are even, then f of x1 equals x1 over 2 and f of x2 equals x2 over 2. How do we check from here that these values are not equal? Well, since we chose x1 not equal to x2, we can divide both sides by 2 and see that the equation remains true. And we finally conclude that f of x1 is not equal to f of x2. We follow up with the second case. If both x1 and x2 are odd, then f of x1 equals 1 minus x1 over 2, and f of x2 equals 1 minus x2 over 2. Again, since x1 is not equal to x2, this means negative x1 is not equal to negative x2. Then, we add 1 to both sides of the equation and divide them by 2. Since we are doing the same operation on both sides, the equation remains true. Conclusion: f of x1 is not equal to f of x2. Finally, if x1 is even and x2 is odd, it becomes trivial, because f of x1 will always be a positive number and f of x2 will be either 0 or negative. Since a positive number can't be equal to 0 or negative, our conclusion is again that f of x1 is not equal to f of x2. Observe how it isn't necessary to verify the case where x2 is even and x1 is odd, since the process is completely analogous to the case we just analyzed. We successfully studied all possible cases for x1 and x2, and in all of them, we arrived at the same conclusion. This means that x1 not equal to x2 does in fact imply that f of x1 is not equal to f of x2 for all x1 and x2 in n. Hence, f is injective. Now, in order to prove surjectivity, we remember that f is surjective when for all z in z, there exists x in n such that f of x equals z. Again, we need to prove a condition for a universal quantifier, but in this case, we also need to prove the existence of a certain number x. The most common way to prove the existence of an element is by proposing it and showing it satisfies whatever condition we're asking from it. We start then by picking a random number z in z. In this case, given the natural separation of our function between positive and negative numbers, let's try separating into two cases. Either z is strictly positive, or it is less than or equal to 0. If it's positive, then we propose x in n equal to 2z. Notice how x is in fact an element of n, since z is a positive integer, and any positive integer multiplied by 2 is still positive. Now, we can see that after evaluating under f, we get f of x equals f of 2z. Since 2z is always an even number regardless of the value of z, then by definition of f, this equals 2z divided by 2. By cancelling out the 2's, we get back our number z. We conclude then that for any positive integer z, there exists an element x of 2z in n such that f of x equals z. In a similar fashion, if z is less than or equal to 0, we propose x in n as 1 minus 2z. First, we observe that 1 minus 2z is always in n. Given that z is non-positive, then negative 2z will be non-negative, since we're multiplying by a negative number. After adding 1 to minus 2z, we conclude that 1 minus 2z is an integer greater than or equal to 1, hence a natural number. Now we just need to verify that after evaluating in f, we get in return z. And surely so, we notice that f of x equals f of 1 minus 2z. Here, it's important to remember that 1 minus 2z is always an odd number. So, given how we defined our function, f of 1 minus 2z equals 1 minus 2z divided by 2. After a few basic algebra steps, we conclude that this expression equals z. In conclusion, we found x in n such that f of x equals z. For both cases, we were able to find a natural number x that mapped to an arbitrary integer z, which translates into f being surjective. Since we've proven that f is both injective and surjective, that means there exists a bijective function between n and z. Thus, the natural numbers and integers have the same number of elements. How awesome is that? I'd like to finish this video by saying that this is only the very beginning of set theory, arguably one of the most relevant branches in modern mathematics. History usually attributes the label of founding fathers to Georg Cantor and Richard Dedekind. Cantor is known for having devoted a lot of his work into what we call the continuum hypothesis, while Dedekind, on the other hand, is most known for his work on properly defining real numbers through a concept named Dedekind cuts. I won't cover these topics in this video. However, as a little cliffhanger, I'd like to follow up the proof we just made with another question. We've shown that both the natural numbers and integers have the same cardinality. However, what about the real numbers? Is that infinity bigger? What about rational numbers or irrational numbers? These questions led Cantor to develop much of what we consider now fundaments of both set theory and mathematics as a whole. For now, we leave these questions for another time. As always, I hope you found this video useful and entertaining. If you'd like me to cover a certain subject, feel free to leave a comment down below. Thank you so much for watching, and I'll see you all in the next video.